Welcome to another explainer. Today, we're taking a mind-bending journey from the microscopic, squishy world of biology all the way down to the quantum atomic realm. We are looking at two absolute extremes of microscopy. You see, when humanity finally figured out how to actually see these extremes, the living breath of a cell on one hand and the silent, rugged landscape of a single atom on the other, it completely shattered our understanding of how the universe is fundamentally built. Okay, so here's our roadmap. We're going to start by looking at the hard limits of traditional optics. Then, we'll dive right into the living, breathing cellular world before pushing way down to the quantum atomic frontier. After that, we'll put these two monumental technologies in a head-to-head showdown. And finally, look at the real-world business value driving these discoveries.
Section 1. Seeing the unseen. Let's set the stage.
To truly appreciate these extremes in resolution, we first have to understand the historical limits of human sight. How do we observe the invisible? When scientists centuries ago first peered through standard lenses, they were mesmerized by what they found in, say, a tiny drop of pond water or a slice of cork. But they quickly hit a frustrating physical wall. The burning question for generations of researchers became, how do you study what you literally can't even see? How do you map a world that refuses to interact with light in a way our eyes can actually process? The problem was that standard compound microscopes hit a very hard physical limit. Because of the sheer nature of visible light, anything smaller than 0.4 micrometers just wouldn't show up. Plus, transparent living cells are practically invisible. They absorb almost no light as it passes through them. So for decades, biologists faced this heartbreaking trade-off. If you wanted to see the intricate internal structures of a cell, you had to kill the cell, fix it in place, and dye it with heavy chemical stains. Sure, you'd get a beautiful, high-contrast snapshot of the anatomy, but you completely lost the dynamic beating behavior of life. The actual living process remained locked in the dark. Section 2. Phase contrast. This brings us to our first major breakthrough. That sheer frustration of only ever studying dead things is exactly what makes the biologist's ultimate workhorse so important: phase contrast microscopy. The engineering ingenuity here is all in the optical pathway. An annular ring acts kind of like a stencil, shaping the incoming illumination into a hollow cone of light before it passes up through the specimen. That light then travels upward and hits a highly specialized phase ring in the objective lens. This elegant manipulation of light was so revolutionary that the physicist who figured it out, Fritz Cernik, actually won the Nobel Prize in Physics for it in 1953. By separating the direct background light from the scattered light passing through the specimen, the microscope pulls off what honestly seems like an impossible magic trick. It relies entirely on a concept known as a phase shift. Basically, as light travels through transparent cellular structures, say a dense nucleus or fluid cytoplasm, it slows down by just a tiny fraction of a wavelength. This happens because those different parts have different refractive indices. Now, this microscopic delay is completely invisible to the human eye, but think of it like adding heavy, defined shadows to a completely transparent glass sculpture. The carefully engineered phase rings take that invisible delay in time and mathematically convert it into highly visible differences in brightness and contrast. And the result is literally night and day. Where a standard lens just gives you a faint, washed-out smudge, introducing phase contrast makes transparent, living cells suddenly pop with incredible, high-definition internal detail. The paradigm shift for biology was monumental. Suddenly, researchers could literally watch cells divide, move, hunt, and interact in real time, completely undisturbed and without using a single drop of toxic dye. It transformed biology from a science of static snapshots into a cinema of living worlds. Section 3. STM. But what happens when we need to go smaller? Much, much smaller. Welcome to the atomic frontier and the realm of the physicist's ultimate probe, scanning tunneling microscopy, or STM. To go smaller than biology, down to the realm of individual atoms, we have to abandon light and lenses entirely. Instead, we rely on the bizarre rules of quantum mechanics, specifically a phenomenon called quantum tunneling. Under the rules of classical physics, an electron simply shouldn't be able to cross an empty gap without enough energy. It'd be like you or me casually walking straight through a solid brick wall. Strictly impossible. But in the quantum realm, electrons behave like probability waves. If the gap between the microscope's ultra-sharp tip and the sample is thin enough, just a nanometer or so, that probability wave extends right across the void. Against all classical logic, a few electrons will essentially tunnel directly through the empty space to the other side. The crucial point is how brilliantly engineers harnessed that quantum effect. STM uses a microscopic metal wire tip whittled down to literally a single atom at its point. As it approaches within a nanometer of the surface, those electrons start tunneling across the gap, creating a tiny electrical current. A piezoelectric material, which can physically stretch or compress by fractions of an atom when voltage is applied, scans this tip back and forth. And here is where the absolute genius of the feedback loop comes in. As the tip passes over the bumpy topography of individual atoms, the tunneling current tries to spike or drop. The feedback loop instantly detects this and moves the tip up and down over those microscopic atomic bumps to keep the current perfectly steady. The system tracks those minute vertical movements. It acts exactly like a microscopic finger reading atomic braille, feeling its way over the surface to give us a stunning, incredibly precise 3D map of individual atoms. Section 4, the Ultimate Resolution Showdown. Let's see exactly how these two stack up. When we place these two incredible research assets side by side, the vast dichotomy between them becomes super clear. Just look at the sheer difference in scale. Phase contrast operates in micrometers, the bustling microscopic realm of whole living cells. STM operates in angstroms, the unimaginably small, silent scale of individual atoms. And their physical mechanisms couldn't be more distinct, right? Phase contrast elegantly bends physical light waves using optical phase shifts, while STM completely discards light to harness the quantum mechanical tunneling of electrons. Finally, their defining applications. Phase contrast lets us watch the dynamic macrobiological flow of living organisms in real time, whereas STM maps the hard physical topography of atomic surfaces in three-dimensional space. They are completely different tools designed for completely different universes of scale. Section 5. The business of discovery. Why does this actually matter to a modern lab? Beyond pure theoretical science, these tools drive immense financial and strategic value. In simple business terms, phase contrast offers incredibly cost-effective, non-destructive monitoring of living assets. Think about the financial stakes here. If you're growing a multi-million-dollar batch of customized stem cells or testing an experimental pharmaceutical on a live tissue culture, you absolutely need to watch those cells thrive or fail in real time. Destroying a high-value sample just to observe it? That's an unacceptable financial loss. Phase contrast gives you that continuous return on investment. On the other end of the spectrum, STM is the ultimate tool for ultra-high-precision nanoscale R&D. Whether a tech giant is developing next-generation semiconductors, advanced computing chips, or engineering futuristic nanomaterials, STM provides the exact atomic-level quality control required to push the boundaries of material science and secure highly competitive patents. To truly understand the universe, we must master both the macrobiological flow of life and the quantum mechanical precision of the atom. This explainer has taken us from the elegant bending of light through living tissue to the impossible tunneling of electrons across a quantum void. If we can currently visualize both the living, breathing behaviors of a single cell and the electric hum of a single atom, what invisible frontier will be conquered next? Thanks for joining me on this journey, and I hope this gives you a much deeper appreciation of exactly how we see the unseen.